All right. So we'll be going over the first problem. And let's call this, all right, we call it right this here, turn off math suggestions. And we'll be doing the Cartesian coordinate problem for the Laplacian. So this problem is the first, I think, PDE that you're going to be working with. And it basically decomposes into a lot of the original equations that you're very familiar with. So hopefully this will make sense. And this is the first equation we have. And we have the derivatives, or not the derivatives, the boundary conditions, which is going to be this one. And I'll change to another color. The second one is this. The third one is this. Oops. And finally, the last one is this. So these boundary conditions actually have a name to them. Specifically, ones where the derivative is equal to 0, such as these two. This one, are called Neumann boundary conditions. And ones where the value itself is equal to 0 is called the, I call it Dirichlet, but I see this extra I, boundary condition. This might or might not be helpful, but it's good to put a name on things. So next, okay, let's actually retitle this. No. Right. So the first question actually asks, can you draw the domain and boundary conditions? Well, now that we wrote it down, we can simply just draw this out. So let's just have a x and y axis. And then let's do here. Actually, let's put some colors to them. So this is, let's call this x equal to 0. So x equal to 0. And the blue one is going to be x equal 1. The yellow will be y equals 0. And the green will be y equal 1. You might be asking why y equal 1 is at the bottom. This is because I use too much Python and plt.imshow, which is a visualization algorithm, will plot in this format, which I personally don't like but have gotten too used to. Anyways, now that you have this, then we can simply just say that, okay, this is going to be equal to 0. This one is going to be equal to, it's going to be h of x. This one is going to have the derivative, so let's just call this dx equals 0, and then finally this one dy is going to be 0. So that will be part 1a. Let's just erase that. Move this up here for better viewing. Alright, and now let's move on to part B. So the second part asks which direction has homogeneous boundary conditions and which one has non-homogeneous. So this is very similar to what we did with ODEs, right? In ODEs, the homogeneous is basically when the thing that you're being set equal to equals 0. So specifically, you can basically say that the Dirichlet or the Neumann boundary conditions equal 0. So over here, we know that x is always going to be 0, and therefore the x direction is homogeneous. All right, then for here, y direction, so even though one side of the y direction is equal to 0, the other side is equal to h of x, meaning that this is actually not homogeneous. And this can help inform our next step, which is to separate the variables. So let's move on to the third part, which is, okay, now we actually want to solve this Laplacian, or to figure out what phi is. So get basically phi equals something. Well, one thing we can note is that we can always write phi basically as, we can separate the variables. So phi right now is of x and y. Let's actually throw some colors to it. Let's call x anything that is going to be blue and y anything that is, let me see. Oh, I just noticed this was flipped. All right, so y is going to be anything that is yellow. Actually, let's use green. So x and y. And we can actually just directly split this into f of x times g of y. Which makes things very nice because now we can independently solve for these two things. So this is something you can basically always do when trying to solve for PDEs, and this is something you should try to do in the beginning. Now that we have this though, how do you even solve for these? Well, we basically want to isolate each of these variables so that we can solve for them independently. So maybe we can first try to solve for fx equals something, and then gy equals something else. Then we can finally just multiply them and directly get what phi is. To do this, let's note that the derivative, or this Laplacian, is actually directly written as d squared dx squared plus dy squared phi equals 0. And this is kind of nice because now you can just directly plug the above down below. And you'll notice that, okay, this is derivative of x and this is derivative of y. Therefore, what you actually have is that you're only going to be taking the derivative of one term, and the other term is going to be constant with respect to the derivative. So here you can simply, this actually is equivalent to, let's use green first, g of y and d squared dx squared fx equals, or plus f of x d squared dy squared g of y equals 0. And what's also kind of nice about this, just a small tip, is that sometimes I like to write this as this. This saves you like 1 microsecond of writing, but that might be the difference between getting a grade on a test and another grade on a test. Or it just might look a bit nicer. But now that we have this, we can actually try to directly isolate the variables using what we already know about algebra. So how do you isolate these variables algebraically? Well, first you set them to opposite sides, right? So let's set them to opposite sides, and we have gy, and let's put this equal sign here. So we have gy, and then we have something like maybe a negative d squared dy gy. And we have here d squared x and fx. So we just simply took this and then moved this to the other side. All right, well, that variables aren't technically isolated since you're multiplying g by f. So how do you isolate them? Well, you just simply swap the sides by dividing by both of the terms. So you divide by both and you'll be getting, so you divide everything by 1 over fg, and you'll finally end up with this, which is going to be 1 over f dx squared f equals 1 over g dy squared g. And we'll set this actually to, oh wait, I forgot to put this negative. We'll set this to negative lambda squared to solve this equation. And why do we do this? Well, this is actually going to be kind of a inductive step, or we kind of need to know why we're doing this from the beginning. And the idea is that we have this concept, right, that the x direction is homogeneous. So if the x direction is homogeneous, what does this mean? This means we kind of have like something like a sinusoidal pattern, right? We have a 0 condition here, or we have something like this at the derivatives, whatever. And this is going to be nice because now we know that we can write at least the x side in terms of so f of x is going to be equal to something like something sine cosine, from what we've been doing a lot in the past with ODEs. And to get to why we can see this as sine and cosine, well, let's just let's just try to okay, so now that we isolated this, right, let's try to look at this. So let's actually move this back and assume that we already figured out what this lambda was. We have d squared f equals negative lambda squared of f. All right. There's only one set of functions that actually fulfills this requirement very easily. And what is this? Well, let's see. Okay, let's say that this wasn't lambda squared. Let's just say that this was lambda. What is this going to be? Oops, and then let's take the... Okay. Well, this is obviously going to be equal to an exponential, right? So this is going to be e to the lambda x. Why? Because if you take the derivative, then you're going to be getting back itself. So it's going to be e to the lambda x, which is here. All right, so now let's just do this with the second derivative. And okay, well, we know that if we take a derivative 2 times, what is the only function that works for 2 times derivative is basically multiplying by something inside. Well, that's going to be sine or cosine, right? So sine lambda x. And if you take the derivative of that, then it becomes cosine, or becomes lambda cosine lambda x. You take one more derivative, and it becomes negative sine lambda x, which is simply going to be negative lambda squared of the first term. Let's try this for cosine. And we'll see that we get the same relation back. So this is something that you should be able to see just from looking at how this is a second derivative. And from here, then now we can plug this in and we could just say, okay, we're going to be solving for this. Which is nice because now we broke this equation into 2 parts and then we can individually solve for each side. And by solving for each side independently, you actually solve for the full equation. Okay, so let's start with the f side, since this is going to be what we have the homogeneous boundary conditions with. Oops. So let's start with the f side, and I'll just start writing this in white. So for this side, we know that f of 0 equals 0. And from that, then we know that if we have f equals c1 sine lambda x plus c2 cosine lambda x, let's not call this lambda n right now, let's just call this lambda, then 0 is going to be equal to c1 sine of 0 plus c2 cosine of 0 equals 0 plus c2, and therefore c2 equals 0. So f of x is going to be equal to c1 sine lambda x. However, we have another boundary condition. And this second boundary condition will restrict our lambdas to a specific set of numbers. And what is this? Well, this is going to be the derivative condition. So derivative of x is going to be 0, which is going to be the same as lambda c1 cosine x. Well, from here we can rearrange and get, oh yeah, and then this is going to be 1. Okay, f of 1. Then, well, this is not the right way to write it. I'll probably write it like that. Then we have here that lambda equals cosine negative 1 of 0. So we can take out the unit circle and just notice that cosine is only going to be 0 at these points. At these points, cosine is going to be 1. This is going to be negative 1. But 0 is 0. So we just need to figure out what the pattern for getting these points are. And from here, we could just tell that it is going to be 2n plus 1 over 2. And why is that? Well, this is going to be 1/2 when n is 0. Then it's going to be 3/2. So 1/2, 3/2, well, pi. Then it's going to be 5/2, and then so on. So finally, what we get is lambda is going to be dependent on n. So let's do lambda subscript n equals 2n plus 1 over 2 pi, which is going to be our actual answer. And then f x is going to be equal to c1 sine lambda of n x. All right, and now let's move on to G. So let's take out green. So this is G. Well, G is almost the same as F, except one small thing, which is that the signs are flipped. So as you see from here, the sign for the eigenvalue is going to be the same once you multiply by G. And that's going to be important because then you don't use sine for here. You have to use a second derivative that's equivalent to sine and cosine, but is going to be the same sign instead of flipping signs every other time you take a second derivative. And what is that? Well, that's going to be the hyperbolic trig functions. So G is going to be equal to C3 let's call it C3 cosh of lambda n y plus C4 sine or sinh of lambda n y. And similarly, by the boundary condition where dg dy 0, then we can say that g of y is equal to cosh of lambda n y. And finally, for part D then, to get the series representation of the solution, we simply just want to add together all possible combinations of the solution, which is also known as the superposition. And this is going to be phi of xy equals sum and 1. And we could just drop some kind of coefficient across. And this is going to basically represent all of the possible solutions of what we had. And remember how we had this is going to be f times g, right? So we just simply plug in f and g here, where f is going to be c1 sine. However, c1 is a constant, a is a constant, so you don't actually even need to include the c. So let's just call this sine times g, which is going to be cosh. And that is going to be the solution. Oh, and don't forget to write that lambda is 2n plus 1 over 2 pi. Where n is when n starts at 0. Okay, cool. So now that you have this, let's move on to the next part and actually solve for these numbers. So how do you figure out what A is? Well, this goes back to kind of how we deal with ODEs. And we always want to start using the orthogonality condition to figure out how to solve this kind of ODE. The idea is that when you have something like a sine function, it's going to have an area that's what you call odd. And over here, what you'll notice is that across one period, the positive and the negative is going to be equal to the same. So if you integrate over one period, it's going to equal 0. If you multiply this by any kind of number, it's always going to become 0, unless the other number is exactly this, in which case it will become a squared, right? So once it becomes a squared, then you're going to have something that looks more like this, because you're basically taking the absolute value. And what's going to be interesting is that when you do this and get the value of the area of here, you're going to be getting 1/2 of the height, or of not the height, but your integral term. So from here, then we can basically say, okay, let's construct a orthogonality condition, meaning let's construct a integral where we put a test case, right? The test case being sine. So let's compare our full function called h of x, which is going to be h of x equals, is going to be this full thing that we derived before. And over here specifically, we just want to look for a of n. A of n is going to be, let me see. Okay, we're going to be looking for a of n for a general h of x. So we're going to only be comparing to x. Oh, yeah, let me get rid of this y. And if we're comparing to x, then we just need to compare to sine n of x. Or we're basically comparing it to the orthogonal basis of x. And for here, then the idea is that if you multiply these two terms, dx, then you're going to be getting a value of whatever you multiply by. It's going to be equal to 0 whenever n doesn't equal m, and it's going to equal something else whenever it does equal to each other. That something else is going to be 1/2 times the value that isn't being multiplied by. So I think it's gonna be 1/2 times cos times cosh. So let's just write this down to see what this means. So over here you just plug in h, and then you're going to be getting, let's actually take the sum out. So you're allowed to move the sum outside. And you can move this outside the integral too, and you can also move all the y out of the integral, so let's move that out. And I think this is going to be for y is 1. So, well, we want to figure out what this is for y equals to 1. So let's just do that. And now our orthogonality finally is going to be sine mx. And then sine nx dx for n is not equal to m. That is going to equal to, well, whatever we had at the top over here. Okay, so from here, then we have what we have over here, that it's going to be equal to 0. Otherwise, it's going to be equal to 2. So then finally, we can simply, we don't have to actually directly solve for this part or the h part, but we could just say that, okay, once you take this, we have the relationship and this is cosh of m equals 2 times 0 to 1 of hx sine mx dx. And finally, that is going to be how we figure out what a is. And we don't have to actually solve for this, since h could be whatever we plug in. But then this now gives us the flexibility to know what we are looking for. Why is this 2? Well, this goes back to here, this relationship. And specifically, if you do want to look for why this is 2, you can also notice that if you have 2 sine, okay, let's say that m equals n, you're going to be getting sine squared, whatever. And from here, then you actually have a direct trig function that you can change this to if you want to solve the integral. And this is going to be giving you a 1/2. So that is how you figure out the 2 part. And finally, before I stop this, the idea here is that the last step here is you're going to be solving the non-homogeneous boundary condition, and you're basically going to be finding a Fourier series for this function, and this part is basically what you would usually call the forcing.